This video will talk about modeling linear trends, specifically using the regression equation. And then we'll also talk about in section 4.4, evaluating the linear model. Okay, so what's a regression line? It's a tool for making predictions about future observed values. It has the form y equals a plus bx, where a is the y-intercept, b is the slope. Remember that your slope is always going to be attached or to something because it can change, and the intercept is a constant, so nothing is attached to it. Remember this right here, this equation, it should look familiar. It should look something like what you learned in algebra, y equals mx plus b, because that's the function, that's a linear function. And a regression line is usually created with technology, and we'll go through that later on as well. And I just wanted to remind you, we're still talking about like a typical value, right? So before, when we talked about a histogram in chapter 3, a question might be, what's the typical height of a group of people, right? But now, with the regression line, we're able to answer a question a little bit more specific, like what is the typical weight of someone who is 66 inches tall? So again, we're still using the word typical value, and we're still talking about mean. Okay, so here's an example of what a regression equation can do. So it says the scatter plot shows a fairly strong positive linear trend. The regression equation has a slope of 2.16 and a y-intercept of 30.46. The positive trend indicates that players who hit more home runs tend to have more RBIs. So this red line, the regression equation, was created with technology, but I just want to kind of explain to you how it's kind of sort of created without going into too much detail, because then we'd be talking about calculus stuff. But just a quick rundown. Let's say that I just took like a little slice of data, like let's say like right there. So for 30 home runs, you see that there's variation, right? There's not just one dot, but there's a bunch. So what this regression line does is, for all of the slices in here, it just goes and it takes the average of all of those. Maybe I'll use a different color for that. It takes the averages, right? So this is like all averages along, and then it creates that line based on those averages. So sometimes you'll see that it's also called the line of averages, and that's why. So here's another example. This one shows a negative linear trend. As the age of the car increases, the value tends to decrease. The regression equation is here. So you see how it says predicted value. So remember, now we're always trying to predict the y value. So the y variable here is value in dollars, right? So that's what we're trying to predict. That's always going to be here first in the equation. And I want you to always get used to seeing this predicted, because there's so much variation. Remember, it's like not a guarantee that we're going to get what we get, but we're predicting it to be there. So you might also see something like predicted value. You might see it written like this as well, with this little caret above, and that means kind of like an estimate or prediction. So once we have this equation like we do here, we can input any age we want, replace age there, and then we can make calculations for that age. What is the value of that car? So here is the same exact regression equation from the previous slide, and we're going to use this to make a prediction of a car that is 12 years old. So I just went ahead and rewrote that equation so that I have room down here to work with. And so because we're predicting for a 12-year-old car, what we're going to simply do is we're just going to take out that age, and then we're going to replace that with 12 so that we can make our prediction. So when we calculate this value comes out to $6,795, and that's our predicted value for a car that is 12 years old. Just remember though, right, this is just based on the two variables or the information that we have. There could be other confounding factors or variables that are influencing the value of this car, right? Who knows? The data that we're using could be of only, I don't know, Toyotas. But if we're trying to predict a Honda, the price for a Honda, then it's going to be a little bit different. So remember, when using a regression and we're making predictions, it's just based on what we have. So remember, we can use words like it tends to have a value of $6,795. So we actually found the regression equation in Google Sheets in the last video. But if you don't remember, just go back to that last video. But when in your Google Sheets, after you create your scatter plot, you're going to go to chart editor, and then you're going to look for this use equation part. Once you have that in, it should appear above your graph. Okay, so just here's some notes about the regression that I think you should pay attention to. The order matters. So if you switch the X and Y, so if you switch like height and weight, right, then it's going to completely change your regression equation. So be careful of that. Also, we're always using the X variable to make predictions about the Y variable. So that's why sometimes the X variable is called the explanatory or predictor variable. It's also called independent variable. And the Y variable then is called a response. So explanatory and response variable, and it's also called predicted, predictor and predicted, and then dependent. So normally, right, if you see an X variable called explanatory, the Y value will be called a response. If you see the X variable being called a predictor, the Y variable will be called a predicted. And then if you see the X variable being called independent, the Y will be called dependent. Okay, so whenever you have that regression equation, it's important that you can interpret all the parts of it. So let's start with slope. So slope tells us how much the Y variable changes when the X variable is increased by 1 unit. A slope close to 0 means there is no linear relationship between X and Y. So here's kind of like the formula that we can use to calculate slope. And I'm going to kind of explain this to you. So normally in algebra, if you remember, for slope, we will be finding the change in Y over the change in X. Kind of similar, but now for statistics, because we have variation in the data, and we're not just working with a linear function, it's a straight line. Now you're going to ask yourself how much Y deviates over how much X deviates. And that's why when you see in the formula, we're working with standard deviation, right, instead of just an X or a Y, because there's so much variation going on that we want to know how much the Y is deviating over, or that ratio of how much is deviating over how much X is deviating. So next question is, why do we multiply by R? Well, if you remember, what is R? That tells us the strength of the association, right? Now, if we didn't have R in there, how would we know if it's positive or negative? Because if you remember, your standard deviation is always going to come out positive. We have functions in place in the formula so that it does so, right? But sometimes our slope is not going to be positive. Sometimes it's going to be negative. So how do we know? That's why we multiply it by your R value, right? It might have an R value of negative 0.46, right? This is going to put it in terms of a positive or a negative for us. I'll also do a quick sketch real quick just to see and give you a visual of what we're doing to find the slope. So let's say this is your regression line, and you have all these dots, right? We're trying to find out how much the Y variable is deviating over how much the X variable is deviating, and that will give you the steepness or the slope of your regression. So here's an example for interpreting slope. Regression equations show the association between age of the car and the value. So this is the same regression equation that we were previously working with. So the slope right here is 1,215. We're going to interpret that slope. So here's your interpretation. What's happening to the Y as the X changes? So here's interpretation for each additional year of age, right? Year is your X variable. The value of the car tends to decrease by 1,215. Remember, this is what we're trying to predict. We're trying to predict the Y variable, which is the value. So for each additional year of age is associated with a decrease of 1,215 in value. So whenever interpreting the slope, remember you're interpreting it in terms of 1 unit of x variable, either increase or decrease, depending if it's positive or negative, right? Just like how we have here decrease, because this is a negative slope. Okay, so now let's interpret the y-intercept. The y-intercept is the predicted value when x is 0, right? So in your graph, all these points along this axis could be an intercept, right? So it's intercepting the y-axis, and that's the y-axis. So let's say, I don't know, I call this first point 0, 1. Then the next point would be 0, 2. Right, if I went all the way to, I don't know, 1,000, right? It would be 0, 1,000. No matter what point or where you are on this y-axis, your x variable or your x value is always going to be 0. So what does the y-intercept predict? Well, it predicts what's happening when your x is at 0. So for example, like age 0, when someone is first born, or when the car is first made, what's the value when it's first made, right? When it's at 0. So the y-intercept is meaningful only if it makes sense. Sometimes it just won't make sense. And you'll see later on how sometimes this y-intercept just won't make sense. Okay, here's an example to interpret the y-intercept. So using the same exact regression equation, and this time we're going to focus on the y-intercept instead of the slope. So our y-intercept at 21,375. So interpret the y-intercept. So remember, this is the value when x is at 0. And our x variable that we're talking about here is age. And we're talking about a car. So let's interpret that. It's the predicted value when x, which is the age, is at 0. In other words, when the car is new, its value is 21,375. So that makes sense, right? That the slope is negative, because as the car ages, the value is going to decrease. So it might look something like this, I don't know, in the graph, where here's your graph, and it's a negative trend, right? So this would be like where the y-intercept is at 21,375, and that's when x is at 0. That's the brand new car. And then as time goes by, the value of the car is going to decrease. Okay, let's look at another example to interpret that y-intercept. In a previous example we used, this was in the last video, we talked about an association between height and weight in women. And here is what the regression equation is. I would just add predicted weight. Make sure we're using that predicted, right? So predicted weight, at negative 442.882 plus 9.03 times height. I like to add that parenthesis so I know I got to multiply. Interpret the y-intercept if appropriate. Okay, so y-intercept, we're talking about height and we're talking about weight. So it's the predicted value for weight if x, which is the height, is 0. So this one just kind of doesn't make sense because it's impossible to weigh negative 442 pounds. Like, this is meaning it's a weight. It's also impossible for a woman to be 0 inches. Like, you're taller than 0 inches the second you're born, right? So this is an example of a y-intercept that doesn't make sense to interpret. It's just not helpful for us. So if this happens with your regression analysis, you could just report this is the y-intercept. However, it's not useful or important for me to interpret. Okay, so now we're at the last section in chapter 4, evaluating the linear model. So here are some cautionary notes about regression. Don't use linear models to describe nonlinear associations. Always look at the scatter plot first. So remember, previously in the other video, we talked about make sure that we're working with something that's linear. How do you know? You have to graph it, because let's say that you have something that you graph and it's a changing trend, right? It's going to go up and then it's going to go down. It's nonlinear. Well, if it's nonlinear, it just doesn't make sense to fit some kind of regression line in there. It doesn't make sense at all. So we have to make sure that the shape is linear first. Another thing is correlation is not causation. This is super important. And we talked about this even in fact in chapter 1. Right? Just because you find a correlation, it doesn't mean something is causing something else to happen. Remember causality, right? So it just means there's an association. So if you find that the age of the car is going down as time goes by, right? You have a negative association. That doesn't mean that the age is causing the value to go down. There could be other factors that influence it. So whenever describing scatter plots, you never use the word cause or cause and effect. You can just say there's a strong association or a trend. Okay, so the next one is be aware of outliers. And this has been consistent for us throughout the start of the course, right? Always look if there's some kind of outlier going on, like you might have a bunch of scatter, and then boom, you have a dot that's like all the way out here. That's weird, it's strange. Check it out, figure out where it's coming from. And then the last one is don't extrapolate. So don't make predictions beyond the range of the data because we're not sure that the linear trend will continue. So for example, like if your data range only goes, actually let me erase that. If your data range only goes to a certain point, like the car, the value of the car, so that one was a negative trend, right? So something like that. You don't want to extrapolate, meaning like you don't want to make a prediction for an age that's outside of your data range here because you don't know what's happening. Like maybe it's not going to continue to go down after this point. Maybe it's going to just start to like level off. We don't know that because we don't see the rest of the data. So it says don't extrapolate. Now in real situations, like extrapolating happens, right? Like in the year 2050, this is what CO2 levels are going to look like if we don't change. That's an extrapolation, but that's done with caution, right? That's saying if we continue on this trend or if these other factors don't influence our data, right? That's okay. So here is an example for extrapolation. In a previous example, we found there was a strong linear relationship between heights and weights in women. Regression equation is shown. What weight does this equation predict for a woman who is 36 inches tall? Okay, so here is what happened when we input our 36 inches and we use the regression equation to make a prediction. We come out with negative 117.8 pounds. Just doesn't make sense, right? Like the range of the data was for women only for 61 to 68 inches tall. It's not appropriate to use it for someone who is 36 inches tall since 36 is beyond the range. So 36 inches tall, like it's not in the range. And if we're only looking here, it doesn't make sense to extrapolate and use 36 because also someone who is negative 117 pounds, that's why you're getting a result that just doesn't make sense because it's an extrapolation. So the very last thing we're going to talk about in chapter 4 is the coefficient of determination, or in other words, r squared. So remember we talked about the r value before, and this is very, very similar. So it's just squaring that r value. It's usually converted to a percentage. So when you report r squared, always use a percent between 0% and 1%. And here's why. Because it measures how much variation in the response variable is explained by the explanatory variable. The larger r squared, the smaller the amount of variation in the scatter. So for example, let's say that we have some kind of scatterness in the data, right? If we're talking about R tells us how strong of an association we have going on here, like how linear is it? But now if we go ahead and we fit a linear regression line on it, r squared is telling us how well does this line fit the scatterness of the data. That's why it can only be from 0 to 100%, because you can't say like this line is just fitting negative percent with the data. It doesn't make sense. So anywhere from 0% to 100%. Also too, if you remember in the last video, I had you guys click on show R squared when we created the scatter plot graph, right? So that brings it up in Google Sheets and it's there for you. And you can also get the R value from that R squared. And here's how to do that. So last example, for the data on car age and predicted value, R is negative 0.778. So you should kind of have a picture in your mind what this graph's looking like, right? It's a negative trend. It's a kind of relatively strong negative trend because 0.778. Now we're going to compute and interpret R squared. So you're just basically taking this R value and squaring it. This should kind of be like a tiny squared, not multiplied by 2, but so square that value. And then we come out with 0.605. And then when we convert that to a percentage, we got 60.5%. So here's how you can interpret it. Car age explains about 60.5% of the variation in the car value. So remember, we're trying to always predict the Y variable, which is car value. And so we're trying to predict it based on the X variable. So this is showing us how well this prediction of the value of the car is based on the age of the car.